The units of a rate constant K aren't the same as the units of rate. The units of K depend on the overall order of the reaction. They are different for reactions with different overall reaction orders, as can be seen from the table below. Make K the subject of the equation. That is, to make it alone on one side of the equation and get all the other terms on the other side of the equation. Substitute appropriate units for each term. The units for rate is molar per second. The units for reactant concentration is molar, and units for reactant concentration square is molar square. Then simplify units by cancellation if possible. There are three critical things to remember about rate law. The exponents or powers in a rate law must be determined from a set of experimental data. Comparing changes in individual reactant concentrations with changes in rate shows how the rate depends on each reactant concentration. Reaction order is always defined in terms of reactant concentrations, never product concentrations. Experimental determination of the rate law. Graphical approach to determine order of reaction. The order of a reaction may or may not have a bearing on the reaction rate and can also be deduced through a graphical approach using concentration versus time graph and or rate versus concentration graph. For zeroth order with respect to one reactant, the concentration of the reactant has no effect on the rate of reaction. Rate equals rate constant K times concentration of A raised to the power of 0. Any number raised to the power of 0 is 1. Hence, rate equals K times 1. Rate equals K. K is the rate constant. As the word constant means an unchanging number, when rate equals K, rate stays the same and does not change. In the rate against concentration graph, K is an unchanging value, so the graph is a horizontal straight line with the same rate at different concentrations of reactant A. In the concentration against time graph of a zeroth order reactant A, the gradient is the final concentration minus initial concentration of A divided by final time minus initial time. This is change in concentration of A over change in time. The slope is negative since the reactant is being consumed. Since the graph is a straight line graph, any 2 points on the graph used to determine the gradient give the same value. That is, the gradient is constant. The negative gradient times minus is the rate as well as the rate constant. For first order with respect to one reactant, the reaction rate is only proportional to the concentration of a single reactant. The rate law is K times concentration of reactant A raised to the first power. The rate versus concentration graph is a straight line graph of the form y is equal to mx plus c, where c, the y-intercept, is 0. Rate is the y-axis, concentration is the x-axis, K is the constant gradient m. The concentration versus time graph is a curve whose slope starts off as steep, then progressively becomes gentler as the reactant concentration drops as more of it is consumed. The slope is negative. For second order with respect to one reactant, the reaction rate is proportional to the square of the concentration of a single reactant. The rate law is K times concentration of reactant A raised to the second power. The rate against concentration graph is a curve akin to y equals to ax squared. Rate is the y-axis, concentration is the x-axis, K is A. The concentration against time graph is a curve whose slope starts off as steep. Reactant A is consumed rapidly, so its negative slope is steeper than that of a first-order reactant.